Hello students, welcome back. Find a comfortable position. Whether you're lying in bed, relaxing on the couch, or settling in for the evening, tonight we have another gentle lecture prepared for you. One designed so you can simply listen, learn, and let yourself drift off whenever sleep finds you. There's no pressure here, no tests, no deadlines. Just knowledge flowing softly in the background as your mind gradually winds down. Some of you will absorb these concepts while dozing. Others will fall asleep within minutes, and that's perfectly fine. Learning doesn't always require intense focus. Sometimes it happens in those twilight moments between waking and dreaming. If you're enjoying these sleepy lectures, I'd appreciate a quiet like on this video. It helps other students find this peaceful corner of the internet. And if you feel like it, leave a comment below, letting me know where in the world you're listening from tonight. I'd really like to know where my students are. Whether you're in Tokyo as the sun rises, in London as evening falls, or somewhere in the American heartland, in the depths of night. It brings me comfort knowing we're all here together, scattered across the globe, learning in the quiet hours. Now that we understand how humanity came to recognize the Milky Way as a galaxy, let us explore its structure in detail. Let us take this vast, complex system and break it down into its component parts, examining each one carefully, like a naturalist studying the anatomy of some magnificent creature. The Milky Way is not a uniform blob of stars. It has structure, organization, different regions with different characteristics. If you could step outside the galaxy and view it from a distance, you would see these distinct components clearly. Since we cannot actually do that, we must piece together the picture from observations made from within, like archaeologists reconstructing an ancient building from fragments. The most prominent feature of the Milky Way is the disk. This is the flat, pancake-like structure I mentioned earlier, stretching about 100,000 light years from edge to edge. The disk is where most of the galaxy's stars reside. It is also where most of the gas and dust can be found, the raw material from which new stars form. The disk itself has structure. It is not a smooth, featureless plane. Instead, it contains spiral arms, long, graceful curves of stars, and glowing gas that wind outward from the center. These spiral arms are one of the most beautiful and distinctive features of spiral galaxies. They give the Milky Way its characteristic appearance, though as I have said, we cannot see this appearance directly from our vantage point inside. The spiral arms are not solid structures. They are not like the arms of a starfish, permanently attached and rotating as a unit. Instead, they are more like waves or patterns moving through the disk. Stars drift in and out of the spiral arms as they orbit the galactic center. The arms persist over time, not because the same stars always occupy them, but because stars crowd together in these regions, making them appear brighter. Think of it like a traffic jam on a highway. Cars enter the jam from behind, slow down, then accelerate and leave from the front. The jam itself, the region of slow-moving traffic, persists in one location, even though the individual cars are constantly changing. The spiral arms work in a similar way. They are regions of higher density, where stars and gas are compressed together, and this compression triggers the formation of new stars, making the arms glow bright. Our own Sun is located in a minor spiral arm called the Orion Arm, or sometimes the Orion Spur. It is a smaller structure connecting two of the major arms, the Sagittarius Arm and the Perseus Arm. From our position in the Orion Arm, we orbit the galactic center at a distance of about 26,000 light-years, taking roughly 225 million years to complete one full revolution. Within the disk, astronomers distinguish between two populations of stars, which they call somewhat unimaginatively Population 1 and Population 2. Population 1 stars are relatively young. They are found in the spiral arms and in the thinner parts of the disk. They are metal-rich, which in astronomy means they contain significant amounts of elements heavier than hydrogen and helium. Our Sun is a Population 1 star. Population 2 stars, by contrast, are old. They are metal-poor, containing far fewer heavy elements. They are found in the thicker parts of the disk, in a region called the thick disk, and in the halo, which we will discuss shortly. Population 2 stars formed early in the galaxy's history, when there had not yet been many generations of stars to produce and scatter heavy elements. The disk is where the action is, so to speak. It is where stars are being born, where supernovae explode, where the chemical elements are being mixed and redistributed. It is a dynamic, evolving environment. Above and below the disk, the galaxy has a different character. If you were to travel perpendicular to the disk, moving either up or down from the plane, you would pass through the thick disk and eventually enter a region called the stellar halo. The halo is a roughly spherical distribution of stars surrounding the entire galaxy. It is much less dense than the disk. Stars in the halo are spread far apart, with vast empty spaces between them. If you lived on a planet orbiting a star in the halo, your night sky would be lonely and dark. There would be no Milky Way band, no rich fields of stars, just isolated points of light scattered across the void. The halo contains some of the oldest stars in the galaxy. These stars formed more than 10 billion years ago, in the early stages of the Milky Way's history. They are survivors, ancient witnesses to the galaxy's youth. By studying these stars, their compositions and their motions, we can learn about the conditions that existed when the galaxy was forming. The halo also contains globular clusters. These are dense, spherical collections of stars, each cluster containing hundreds of thousands to millions of stars packed tightly together. Globular clusters are beautiful objects. Through a telescope, they appear as fuzzy balls of light, brightest at the center where the stars are most crowded. If you could travel to a planet in the core of a globular cluster, the night sky would be ablaze with stars. Thousands of stars would be brighter than Venus appears from Earth. You would be able to read by their combined light. There are about 150 to 200 globular clusters orbiting the Milky Way. They follow long elliptical orbits that carry them far above and below the galactic disk. Like the halo stars, the globular clusters are old, dating back to the galaxy's formation. They are time capsules, preserving information about the early universe. Now let us move inward, toward the center of the galaxy. As we approach the middle, the disk begins to thicken and brighten. Stars become more numerous. The density of matter increases. We are entering the region called the bulge. The bulge is a roughly spherical or ellipsoidal concentration of stars at the galaxy's center. It is old, like the halo, containing primarily population 2 stars. The bulge is crowded. stars are packed much more tightly than in the disk. If we lived in the bulge instead of the disk, the nearest star to our Sun might be only a light year away, or even less, instead of the 4 light years that separate us from Proxima Centauri. The Milky Way's bulge has a particular shape. It is not a simple sphere. Instead, it is elongated into a bar, a rectangular or peanut-shaped structure that extends from the center. This bar is made of stars orbiting in elongated paths. The bar rotates as a unit, slower than the disk, but still turning over the course of hundreds of millions of years. Bars are common in spiral galaxies. About 2/3 of all spirals have them. They play an important role in galactic dynamics, funneling gas inward toward the center where it can fuel star formation, and, as we will discuss later, feed the central black hole. At the very center of the bulge, at the exact middle of the galaxy, lies something extraordinary, a supermassive black hole. We call it Sagittarius A star, or SGR A star for short. It has a mass of about 4 million times the mass of our Sun, all compressed into a region smaller than the orbit of Mercury. We cannot see this black hole directly. Black holes by definition do not emit light, but we can see its effects. We can watch stars orbiting around it, moving in elliptical paths at tremendous speeds. Some of these stars approach to within a few light hours of the black hole, traveling at a few percent of the speed of light. By tracking these orbits carefully over many years, astronomers have been able to determine the mass of the invisible object they orbit. The only thing that can be so massive and so compact is a black hole. We will return to Sagittarius A star later and discuss it in more detail. For now, simply note its presence. It sits at the center of the galaxy, a dark gravitational anchor around which everything else revolves. So far, we have discussed the visible components of the Milky Way: the disk, the bulge, the halo, the globular clusters. But there is another component, far more massive than all the others combined, and yet completely invisible. This is the dark matter halo. Dark matter is one of the great mysteries of modern astronomy. We do not know what it is made of. We have never detected a dark matter particle directly, and yet we know it must exist, because we can see its gravitational effects. The evidence for dark matter in the Milky Way comes primarily from studying the rotation of the galaxy. In the 1970s, the astronomer Vera Rubin and her colleagues measured how fast stars and gas orbit at different distances from the galactic center. They expected to find that objects farther from the center orbit more slowly, just as the outer planets in our solar system orbit more slowly than the inner ones. But that is not what they found. Instead, they discovered that the orbital speed stays roughly constant, even far out in the disk. Objects at the edge of the galaxy orbit just as fast as objects closer in. This was surprising. It meant that there must be additional mass beyond the visible edge of the disk, mass that we cannot see, exerting a gravitational pull that keeps the outer regions moving quickly. This invisible mass is what we call dark matter. It forms a halo around the galaxy, extending far beyond the visible stars. The dark matter halo may extend 10 times farther than the stellar disk, out to distances of perhaps 1 million light years. It contains about 10 times as much mass as all the visible stars, gas, and dust combined. We do not know what dark matter particles are. They do not interact with light, which is why we cannot see them. They do not interact strongly with ordinary matter, which is why we have not detected them in laboratories despite decades of searching. They interact only through gravity, pulling on ordinary matter and shaping the structure of galaxies. The dark matter halo is the scaffolding of the Milky Way. It provides the gravitational framework within which the visible galaxy formed. Without dark matter, the Milky Way as we know it could not exist. The disk would fly apart, the spiral arms would dissolve, the stars would scatter into the void. It is humbling to realize that most of the galaxy's mass is in a form we do not understand. The stars and gas that we can see, the beautiful spirals and glowing nebulae, are just the visible tip of a much larger structure. We are like someone examining an iceberg, seeing only the part above water and having to infer the much larger mass below. Let us now consider the overall mass and scale of the Milky Way. As I mentioned earlier, the galaxy contains between 100 billion and 400 billion stars. The wide range reflects genuine uncertainty. It is difficult to count stars when you are inside the galaxy, and much of it is hidden behind dust. The total mass of all the stars is estimated to be about 60 billion times the mass of the Sun. This sounds like a lot, and it is, but it is only a small fraction of the galaxy's total mass. There is also gas and dust between the stars. The interstellar medium, as it is called, contributes another 10 to 15 billion solar masses. Add in the dark matter, and the total mass of the Milky Way is somewhere between 1 and 2 trillion solar masses. Most of that mass, as I have said, is dark matter. The visible matter, the stars and gas we can actually see, accounts for less than 10% of the total. The Milky Way is not static. It is a dynamic, evolving system. Stars are being born in clouds of gas and dust. Old stars are dying, some gently puffing off their outer layers, others exploding as supernovae. The spiral arms are sweeping through the disk, compressing gas and triggering waves of star formation. The bar is funneling matter toward the center. Satellite galaxies are being torn apart by tidal forces and absorbed into the main body of the Milky Way. All of this is happening on timescales far longer than a human lifetime. A star like the Sun takes millions of years to form. It lives for billions of years. The spiral arms take hundreds of millions of years to complete one rotation. The processes that shape the galaxy are slow, patient, inexorable. And yet, from our human perspective, we can observe snapshots of these processes. We can see clouds collapsing to form stars. We can see young stars lighting up the gas around them. We can see the remnants of supernovae, expanding shells of hot gas rushing outward into space. We can piece together the story of the galaxy's evolution by studying objects at different stages of their life cycles. Our solar system is a part of this larger story. The Sun and planets formed about 4.6 billion years ago from a cloud of gas and dust in the galactic disk. That cloud was already enriched with heavy elements from previous generations of stars. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was forged in the cores of stars that lived and died before the Sun was born. We are made of recycled stardust. This is not a metaphor. It is a literal fact. The atoms in our bodies have been part of the galaxy for billions of years, cycling through stars and interstellar clouds, mixing and recombining, until finally they came together to form the planets, and eventually life. The Milky Way is not just our home in a geographic sense. It is our origin. We are products of the galaxy's chemical evolution. Our existence depends on the processes that have shaped the galaxy over cosmic time. Our position in the galaxy is not particularly special. We are not at the center. We are not at the edge. We are in the disk, about halfway out, in a minor spiral arm. There is nothing unique about our location, and yet it is a good location for life. We are far enough from the center to avoid the intense radiation and frequent supernovae that characterize the bulge. We are in a region where heavy elements are abundant, allowing the formation of rocky planets. We orbit at a speed that keeps us in a relatively stable position between spiral arms, avoiding the violent star formation regions. In a sense, we are in a quiet suburb of the galaxy, a calm, stable neighborhood where stars like the Sun can live long lives and planets can evolve complex chemistry and, eventually, life. As we orbit the galactic center, we move through different regions of space. We drift slowly toward and away from spiral arms. We bob up and down through the disk, crossing the midplane every 30 million years or so. These motions expose us to changing environments, variations in the density of stars and gas and cosmic rays. Some researchers have speculated that these changes might have effects on Earth. Perhaps passing through a spiral arm increases the rate of supernovae, which in turn increases the flux of cosmic rays, which might affect Earth's climate or the rate of mutations and evolution. These ideas are speculative, and the evidence for them is mixed, but they illustrate an important point. We are not isolated from the rest of the galaxy. We are part of it, influenced by it, connected to it. The Milky Way is a spiral galaxy. I have said this several times now. But what does that mean exactly? What is a spiral galaxy? Spiral galaxies are one of the main types of galaxies in the universe. They are characterized by a flat disk with spiral arms, a central bulge, and often a bar. The Milky Way fits this description. It has a disk, spiral arms, a bulge, and a bar. It is a barred spiral galaxy, which astronomers classify as type S, B, C. The S means spiral, the B means barred, and the C indicates that the spiral arms are loosely wound, rather than tightly wound. Not all galaxies are spirals. Some are elliptical, shaped like footballs or spheres, with no disk and no spiral structure. Elliptical galaxies tend to be older and contain primarily old stars. They have little gas and dust, so they are not forming new stars. They are, in a sense, retired galaxies, living on the stellar population they formed long ago. Other galaxies are irregular, with no clear structure at all. These are often small galaxies that have been disrupted by gravitational interactions with neighbors. The Milky Way is a fairly typical spiral galaxy. It is not the largest galaxy in the universe, nor the smallest. It is not the most active, with intense star formation and a vigorously feeding black hole, nor is it dormant. It is, in many ways, an average spiral galaxy, and that is part of what makes it so valuable for study. By understanding a typical galaxy, we learn about galaxies in general. Let me take a moment to talk about distance scales within the galaxy. When we discuss the Milky Way, we are dealing with distances that are difficult to comprehend intuitively. A light year is already an enormous distance. Light travels 186,000 miles per second. In 1 year, that amounts to about 6 trillion miles. The Milky Way is 100,000 light years across, That is 600 quadrillion miles. That is a 6 with 17 zeros after it. To put this in perspective, if you were to travel to the galactic center at the speed of a modern spacecraft, say 25,000 miles per hour, it would take you about 750 million years to get there. If you wanted to cross the entire galaxy, it would take 1.5 billion years. These are not practical journeys. These are not even imaginable journeys in any human sense. And yet, light makes these journeys. Photons of light, traveling at their cosmic speed limit, cross the galaxy in 100,000 years. When we look at a star 1,000 light years away, we are seeing light that left that star 1,000 years ago. We are looking back in time. The star might have changed in the intervening centuries. It might have dimmed or brightened. It might have moved to a different location. We will not know until the light from its current state reaches us. This time delay is built into all astronomical observations. We are always looking at the past. For nearby stars, the past is only a few years ago. For distant stars in the galactic halo, it might be tens of thousands of years ago. For other galaxies, it can be millions or billions of years. Astronomy is, in a very real sense, a form of time travel. We use light as a time machine, peering backward to see the universe as it was. The structure of the Milky Way that I have described, the disk and bulge and halo, is not static. It has evolved over time. The galaxy was not always as it is today. In the distant past, billions of years ago, the Milky Way was smaller and less organized. It has grown over time through the gradual accumulation of gas and through mergers with smaller galaxies. Evidence for this growth can be seen in the halo. The stars and globular clusters in the halo have a wide range of orbital motions. Some orbit in the same direction as the disk. Others orbit in the opposite direction or at steep angles. This chaotic motion suggests that the halo was assembled from the debris of many smaller systems, each of which contributed its own stars and imparted its own angular momentum. The Milky Way is still growing today. It is currently in the process of absorbing several small satellite galaxies. The largest of these is the Sagittarius dwarf elliptical galaxy, which is being pulled apart by the Milky Way's gravity. Streams of stars from Sagittarius can be traced looping around the Milky Way like ribbons. Over time, these streams will disperse and the stars will become part of the Milky Way's halo. This process of galactic cannibalism is common in the universe. Large galaxies grow by eating smaller ones. It is a slow, gentle process, at least on cosmic scales. The stars from the smaller galaxy are not destroyed. They are simply incorporated into the larger system. Over billions of years, they will forget their origin and become indistinguishable from stars that formed in the Milky Way itself. Our own galaxy, then, is not a pristine, isolated structure. It is a patchwork assembled over time from many smaller pieces. The halo in particular is a graveyard of ancient galaxies, their individual identities erased but their stars still orbiting, bearing witness to a violent past. In summary, the Milky Way is a complex, multi-component system. It has a flat disk where most of the stars reside and where new stars are still forming. It has spiral arms that wind through the disk. It has a central bulge, elongated into a bar, crowded with old stars. It has a spherical halo of ancient stars and globular clusters. And it has a massive dark matter halo, invisible but gravitationally dominant, providing the framework that holds everything together. Understanding the structure has taken centuries of patient observation and careful reasoning. We have had to piece together the picture from within, using every tool at our disposal. And yet, despite the challenges, we have succeeded. We know the shape of our galaxy. We know its size, its mass, its components. We know where we fit into this vast structure. It is a remarkable achievement, and it is only the beginning. In the sections to come, we will dive deeper into specific aspects of the galaxy. We will visit the central black hole. We will explore the spiral arms and the processes of star formation and death. We will examine the galaxy's dynamics and its interactions with neighbors. We will discuss the methods we use to study the Milky Way and the questions that remain unanswered. But for now, let us pause and appreciate what we have learned. The Milky Way is our home, a beautiful and complex structure shaped by billions of years of cosmic evolution. It is a dynamic system, still growing, still changing, still creating new stars from the ashes of the old. And we are part of it, intimately connected to it, products of its long history. Let us rest here for a moment before continuing our journey deeper into the heart of the galaxy. We now turn our attention to the heart of the galaxy, the galactic center. This is a place unlike anywhere else in the Milky Way, a crowded, violent, energetic environment where stars orbit at tremendous speeds and radiation floods through space. And at the very center, invisible yet undeniable, sits a supermassive black hole. The galactic center lies about 26,000 light-years away from us, in the direction of the constellation Sagittarius. We cannot see it with our eyes. Even with the most powerful optical telescopes, the center remains hidden. This is because of dust. The interstellar dust that fills the galactic disk absorbs visible light, blocking our view. If you look toward Sagittarius on a dark night, you will see the Milky Way band is interrupted by dark patches. These are not empty regions. They are dense clouds of dust, silhouetted against the background stars. The dust absorbs and scatters blue light more efficiently than red light. This is why distant stars sometimes appear reddened. The same reason sunsets on Earth appear red. But for the galactic center, the dust is so thick that even red light cannot get through. Visible light is almost completely blocked. To see the galactic center, we must use other wavelengths of light. Infrared light, with its longer wavelength, can penetrate dust more effectively. Radio waves can pass through dust almost as if it were not there. X-rays and gamma rays reveal the most energetic processes. By observing the galactic center at many different wavelengths, astronomers have pieced together a picture of this hidden realm. What they have found is extraordinary. The central few light years of the galaxy contain millions of stars packed tightly together. The density of stars here is thousands of times higher than in our neighborhood. If we live near the galactic center, the night sky would be brilliant with stars. The nearest star might be just a few light weeks away instead of light years. Hundreds of stars would be bright enough to cast shadows, but living near the galactic center would be dangerous. The region is bathed in intense radiation. High-energy photons stream from hot stars and from matter falling toward the central black hole. Cosmic rays, charged particles accelerated to nearly the speed of light, permeate the environment. Any planet in this region would be bombarded constantly. The radiation would strip away atmospheres, sterilized surfaces make the emergence of life extremely difficult, if not impossible. The stars near the galactic center are not like the Sun. Many of them are massive young stars, dozens of times more massive than the Sun, burning bright and hot and blue. These stars live fast and die young. They exhaust their nuclear fuel in just a few million years, then explode as supernovae. The rate of supernova explosions near the galactic center is much higher than in the disk. There are also older stars near the center, red giants and evolved stars nearing the end of their lives. And there are dense stellar remnants, neutron stars and black holes left behind after massive stars explode. The galactic center is a cosmic junkyard in some ways, littered with the debris of countless stellar deaths. At the exact center of all this, at the precise gravitational middle of the galaxy, is Sagittarius A star, SGR A star for short, a supermassive black hole with a mass of approximately 4 million solar masses. Let me pause and explain what that means. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. Black holes form when a large amount of mass is compressed into a very small volume. The boundary around a black hole, the point of no return, is called the event horizon. Once something crosses the event horizon, it is lost forever. It cannot send signals back to the outside universe. It is cut off from the rest of space and time. Supermassive black holes are black holes with masses millions or billions of times the mass of the Sun. They are found at the centers of most large galaxies. We do not fully understand how they form. They may have grown from smaller black holes that merged together. They may have formed directly from the collapse of massive gas clouds in the early universe. The details are still being worked out. What we know is that Sagittarius A star exists. We know its mass. We know its location. And we know it is a black hole because nothing else could have that much mass in such a small space. How do we know this? We cannot see the black hole itself. By definition, it emits no light, but we can see the stars around it. And those stars move in very particular ways. Starting in the 1990s, astronomers using infrared telescopes began tracking individual stars very close to the galactic center. They took images year after year, watching how the stars moved against the background. What they discovered was remarkable. Some of these stars are moving at tremendous speeds, thousands of kilometers per second. They trace out elliptical orbits, swinging in close to the center, and then swooping back out. One star, designated S2, has an orbital period of just 16 years. At its closest approach, it comes to within about 17 light hours of Sagittarius A star. That is roughly 4 times the distance from the Sun to Neptune. At this close distance, S2 is moving at nearly 3% of the speed of light. By tracking S2 and other stars like it, astronomers can apply Kepler's laws of orbital motion. The speed and shape of an orbit depend on the mass of the object being orbited. By measuring the orbits precisely, we can calculate the mass of Sagittarius A star. The answer comes out to about 4.1 million solar masses. What could have that much mass? If it were stars, we would see them. The region where Sagittarius A star sits appears dark in infrared images, aside from the orbiting stars. There is no dense cluster of stars at the center. If it were a cloud of gas or dark matter, it would be unstable. Over time, such a cloud would either collapse or disperse. The only stable object that can have millions of solar masses in such a compact region is a black hole. In 2020, the discovery of these orbiting stars and the inference of the black hole's existence was awarded the Nobel Prize in Physics. It was a triumph of patient, careful observation. The astronomers had to track stars over more than 2 decades to see complete orbits. They had to develop sophisticated techniques to correct for the blurring effects of Earth's atmosphere. But the result was definitive. Sagittarius A star is a supermassive black hole. The event horizon of Sagittarius A star, the boundary of the black hole, is about 12 million kilometers across. That is about 17 times the diameter of the Sun. For a supermassive black hole, this is actually quite small. More massive black holes, like those found in the centers of larger galaxies, can have event horizons hundreds of times larger. Despite its mass, Sagittarius A star is relatively quiet. It is not actively feeding on large amounts of matter. Some supermassive black holes are surrounded by swirling disks of gas spiraling inward, heating up and emitting intense radiation as they fall. These are called active galactic nuclei, or AGN. They can outshine all the stars in their host galaxies combined. Sagittarius, a star, is not like that. It flickers occasionally, brightening for a few hours as a small clump of gas falls in, then dimming again. But most of the time, it is quiescent. It is a sleeping giant, waiting. This was not always the case. There is evidence that in the past, Sagittarius A star was much more active. About 6 million years ago, it may have undergone a major feeding event, swallowing a large quantity of gas. The energy released during this event would have lit up the galactic center, creating a brilliant beacon visible across the galaxy. Evidence for this past activity comes from structures called the Fermi bubbles. These are enormous lobes of hot gas extending above and below the galactic disk, stretching about 25,000 light-years in each direction. They were discovered in 2010 by the Fermi Gamma Ray Space Telescope. The bubbles emit gamma rays, the highest energy form of light. The Fermi bubbles are thought to be the remnants of a powerful outburst from the galactic center. Perhaps Sagittarius A star devoured a large cloud of gas, or a star wandered too close and was torn apart. The energy release blew gas outward in 2 jets, perpendicular to the disk, creating the bubbles we see today. The bubbles are still there, still glowing faintly. They are a fossil record of the black hole's violent past. They remind us that even though Sagittarius A star is quiet now, it is capable of tremendous outbursts of energy. In April 2019, astronomers achieved something remarkable. They captured an image of the shadow of a supermassive black hole, not Sagittarius A star, but the black hole at the center of the galaxy M87, a giant elliptical galaxy about 55 million light-years away. The image showed a bright ring of glowing gas surrounding a dark central region. The dark region is the black hole's shadow, the silhouette of the event horizon against the background light. This image was created using the Event Horizon Telescope, a network of radio telescopes scattered across the Earth, all working together to simulate a telescope the size of the planet. It was an incredible technical achievement, and it provided direct visual evidence of a black hole's event horizon. In May 2022, The Event Horizon Telescope released a similar image of Sagittarius A star, our own galactic center black hole. The image looks remarkably similar to the M87 image, a bright ring of emission with a dark center, the shadow of the black hole. Seeing this image was profound. For years, we had inferred the existence of Sagittarius A star from the orbits of stars around it. But now, we could see it. Or rather, we could see its absence, the dark void where light cannot escape. It was a direct confirmation of the black hole's existence and a stunning demonstration of the power of modern astronomy. The region around Sagittarius A star is not empty. There is gas and dust swirling around the black hole, heated to millions of degrees. This hot gas emits radiation across the spectrum, from radio waves to X-rays. By studying this emission, astronomers can learn about the environment near the black hole and the processes by which it feeds. Matter does not fall directly into a black hole. Instead, it spirals inward, forming a disk called an accretion disk. As the matter spirals, it rubs against itself, friction heating it to tremendous temperatures. The inner parts of the accretion disk, closest to the black hole, are the hottest, glowing in X-rays. The outer parts are cooler, emitting infrared and radio waves. The accretion disk around Sagittarius A star is faint compared to those around more active black holes. Not much matter is falling in, but occasionally a cloud of gas or a star on an unlucky orbit gets too close. When this happens, the black hole's gravity tears the object apart. The material is stretched and shredded in a process called spaghettification, a term that sounds whimsical but describes something truly violent. As the material from the disrupted object falls toward the black hole, it heats up and emits a burst of radiation. Astronomers have observed several of these flaring events from Sagittarius A star. They are brief, lasting hours to days, but during that time, the black hole can brighten significantly. There is also a strong magnetic field near the black hole. Charged particles spiraling along magnetic field lines emit radiation, a process called synchrotron emission. This is the source of much of the radio emission we detect from Sagittarius A star. The magnetic field may also play a role in launching jets, narrow beams of particles and energy that shoot outward from the poles of the black hole. We have not yet detected strong jets from Sagittarius A star, but they may exist on small scales. The environment near the black hole is governed by the laws of general relativity, Einstein's theory of gravity. In strong gravitational fields, space and time become warped. Clocks run slower. Light follows curved paths. Orbits precess and wobble in ways that Newton's laws cannot explain. By studying the stars orbiting close to Sagittarius A star, astronomers can test general relativity in one of the most extreme environments in the universe. So far, the theory has passed every test. The orbits behave exactly as Einstein predicted. The star S2, for example, shows a relativistic precession. Its orbit does not close perfectly. Each time it completes a loop, the orbit rotates slightly, tracing out a rosette pattern. This is exactly what general relativity predicts for such a strong gravitational field. These observations are not just academic. They probe the fundamental nature of space and time. They test whether our understanding of gravity holds up under extreme conditions. And so far, it does. General relativity, formulated more than a century ago, continues to describe the universe with remarkable accuracy. The galactic center is also a laboratory for studying stellar dynamics. With millions of stars packed into a small volume, interactions between stars become important. Stars can pass close to each other, exchanging energy and momentum. Sometimes, two stars can collide and merge. Other times, a close encounter can fling a star out of the galactic center at high speed, sending it on a trajectory through the galaxy, or even out of the galaxy entirely. These high-velocity stars, called hypervelocity stars, have been detected. They are traveling at speeds of hundreds or even thousands of kilometers per second, fast enough to escape the Milky Way's gravity. The leading theory for their origin is that they were part of binary star systems that wandered too close to Sagittarius A star. The black hole's gravity captured one star and flung the other away at high speed. A cosmic slingshot. There are also intermediate mass black holes near the galactic center. These are black holes with masses hundreds to thousands of times the mass of the Sun, larger than stellar black holes but smaller than supermassive ones. They may form from the merger of many stellar black holes in dense star clusters. Some of these intermediate mass black holes may be orbiting Sagittarius A star, slowly spiraling inward. Eventually, they will merge with the central black hole, releasing a burst of gravitational waves. Gravitational waves are ripples in the fabric of space and time, predicted by general relativity and first detected in 2015. When two massive objects orbit each other and merge, they shake space itself, sending waves outward at the speed of light. The merger of black holes near the galactic center would produce gravitational waves that future detectors might be able to observe. These waves would carry information about the masses and spins of the merging black holes, and about the warped space-time near Sagittarius A star. The galactic center is a noisy, chaotic place, but it is also a natural laboratory. Nowhere else in the galaxy can we study such extreme conditions. Nowhere else are stars packed so densely. Nowhere else is there a supermassive black hole close enough for us to observe in detail. By studying the galactic center, we learn about the processes that shape the centers of all galaxies. We learn how supermassive black holes interact with their surroundings. We learn how stars behave in extreme environments. And we test the laws of physics under conditions that cannot be reproduced on Earth or anywhere else in the solar system. Let me take a moment to talk about what it would be like to travel to the galactic center. This is, of course, purely hypothetical. The distances involved make such a journey impossible with current or foreseeable technology. But it is worth imagining. If you were to approach the galactic center, the first thing you would notice is the increasing density of stars. As you drew closer, the stars would become more numerous, the spaces between them shrinking. The night sky would grow brighter. Stars that appear faint from Earth would blaze brilliantly. New stars, too dim to see from our distance, would come into view. Within a few thousand light years of the center, the sky would be ablaze with light. Thousands of stars would be brighter than Venus. Hundreds would rival the full moon. There would be no true darkness, even on the night side of a planet. The combined light of all those stars would create a perpetual twilight. Closer still, within a few hundred light years, you would see the effects of the intense radiation. Gas clouds would glow, ionized by the ultraviolet light from hot stars. You would see the remnants of supernovae expanding shells of debris. You would detect X-rays and gamma rays, signatures of violent processes. Within a few dozen light years of the center, individual stars would begin to show visible motion. Over the course of months or years, you could watch stars shift position, their orbital motions around the central black hole apparent even on human timescales. And finally, within a few light years, you would be in the domain of Sagittarius A star. The black hole would dominate the sky, not as a visible object, but as a dark absence surrounded by a ring of glowing gas. You would see stars whipping around it at tremendous speeds, completing orbits in years or decades. You would feel the pull of its gravity, subtle at first, but growing stronger as you approached. If you were foolish enough to continue inward, crossing the event horizon, you would enter a realm from which there is no return. Time and space would switch roles. Falling toward the singularity at the center of the black hole would become as inevitable as moving forward in time. You would be stretched and compressed by tidal forces, torn apart long before you reach the singularity itself. But this is all imagination. In reality, we observe the galactic center from a safe distance, using telescopes and instruments, piecing together what we can from the light and other signals that reach us. The galactic center is a reminder of the extremes that exist in the universe. It is a place of intense gravity, high energy, rapid change, and yet it is also a place governed by the same physical laws that govern the rest of the cosmos. The stars there obey the same laws of motion. The black hole obeys the same theory of general relativity. We can understand it, even if we cannot visit it. As our technology improves, we will learn more about Sagittarius A star and its environment. The Event Horizon Telescope will take sharper images, perhaps even movies showing how the gas around the black hole changes over time. New gravitational wave detectors will listen for the mergers of black holes near the galactic center. Improved infrared telescopes will track more stars, probing closer to the event horizon. Each new observation will refine our understanding. Each new measurement will test our theories. The galactic center is a cosmic laboratory that will continue to teach us about gravity, about black holes, about the extremes of the universe. For now, let us simply appreciate what we have learned. At the heart of the Milky Way, 26,000 light years away, hidden behind veils of dust, lies a supermassive black hole. It is massive, ancient, and mostly quiet. It shapes the orbits of millions of stars. It has sculpted the structure of the inner galaxy, and it waits, patient and inexorable, at the gravitational center of everything we know. It is a fitting heart for our galaxy. Strange, powerful, and profoundly mysterious. A dark anchor around which the Milky Way turns slowly and ceaselessly through the depths of cosmic time. Let us rest here before we continue our journey outward, back into the disk, to explore the processes of stellar birth and death that have shaped the galaxy over billions of years.